I'm Neelkamal Bhuyan, a PhD student at Georgia Institute of Technology, and today I'll be presenting my work on multimodal federated learning with provable guarantees, which I did as an undergraduate student at IIT Bombay with my advisor, Dr. Sharayu Moharir. Federated learning is a distributed form of machine learning where the training happens on the edge devices instead of on the server. The only role of the server is averaging the weights periodically. The local datasets are on the edge devices instead of on the server, and this ensures data privacy. Each round, in each round, the following steps happen. First, the server selects the key clients that will be used for training. Next, each client is assigned a model that it needs to train. Then each client receives the global weights the model it was assigned. It then trains the assigned model on its local training dataset and then sends back the updated weights back to the server. Finally, the server for each model uh, averages the updates it received and creates the new global model. We propose two algorithms for client selection. The first is multi-fed average random, which is an extension of fed average to the multi-model setting. And the second one is multi-fed average round robin, which is a hybrid deterministic stochastic version of multi-fed average random that has greater uniformity over the training process. Now I'll explain how MFRN works. In each round, the set of n available clients is partitioned into m equal size subsets, and then each subset is randomly mapped to a model. This is equivalent to partial device participation of single device fed average. Now I'll discuss how MFRR works. In this case, time is divided into frames, where each frame is defined as a consecutive set of m rounds. At the start of the frame, the set of available clients is divided into m equal size subsets S1 to Sm, and through the m rounds in the frame, the m subsets are mapped to each model in a round-robin manner. Here you can see an illustration how MFRR would work for 4 models. Before going over the theoretical results for MFRN and MFRR, here is an overview of the notations that might be useful. We denote the number of models with M, the number of clients with N, and the set of all clients with S. Further, each client trains a model for E number of local iterations. Finally, we denote the performance metric with delta P of T and which is the expected distance of the current iterate from the optimizer. First, I'll go over the assumptions we make on our loss functions. We assume that the loss functions are smooth and strongly convex. Further, we assume that the expected squared norm of the stochastic gradients are bounded. Further, we make the following assumption, which basically means that the variance of the stochastic gradients is dependent on the sample size of the data used for the stochastic gradient. For more detail on this assumption, you can refer to our paper. For MFRN with decaying step size, we have that the current iterate goes to the optimizer as 1 upon square root t. The proof of this has been done in the form of single model fed average under partial device participation in the paper cited below. We therefore convert the original result into the metric we use by a simple Cauchy-Schwarz inequality. For our client selection algorithm MFRR, we get O of 1 by D convergence for decreasing step size and increasing SGD sample size. Actually, this rate also holds for the case of full client-side GD, but with a better constant factor in the rate. Now we compare multimodal FL with single-model FL and see how multimodal FL is advantageous over single-model FL. We do this by comparing the total number of training rounds required for M models in the multi-model FL setting versus training each of those M models sequentially in the single model FL setting. Now I'll formally define what gain is. It is the ratio of the total number of rounds required for sequentially training the M models to the total number of rounds required by the M models to train simultaneously in the multi-model setting. Each round uses all of the N clients for training, and therefore the above metric used for comparison is fair. Here, we also make the assumption that the M models are of similar computational complexity. Now I'll present the theoretical result we get for gain. For the number of models M less than equal to half of the number of clients and E greater than equal to 2, we get that gain is always greater than equal to 1 and is always increasing with M. Now let's go over the implications of theorem 3. First, we observe that reduction in number of clients used does not severely impact the number of rounds required for target accuracy. Next, the case of A equal to 1. We argue that this case is not usually used in federated learning because it encounters the highest communication cost. Lastly, the M equal to N case. When M is equal to N, each model receives only one client, which is very low when N is large. Now I present the results of simulations we did on quadratic loss functions. Here, each client is a quadratic function in W with the matrix AK and the vector BK designed such that they are uncorrelated across clients. This ensures that there is heterogeneity among the clients, hence mirroring the heterogeneity in federated learning. We analyze these simulations in two ways. First, we compare MFRN and MFRR under constant and decaying step size and see which one performs better. For this purpose, we use the following metric. Next, we plot the trend of gain versus M for various values of E. Rest of time, we do not present the entire set of simulations, but here is a glimpse of what we observed. For the case of M equal to 12 and decaying learning rate, we observe that MFARR has much less variance compared to MFRN, as you can see from the subfigure B. Also from subfigure A, we can see that MFARR performs slightly better compared to MFRN. One might observe that there isn't an order-wise difference between MFARR and MFRand. One possible explanation is that the quadratic minimization problem we simulated does not have SGD but has full gradient descent. Our analysis of MFARR exploits the fact that full gradient descent is being used, but the analysis of MFRand, which is actually Fed average with partial device participation, does not use the advantage of full gradient descent in their analysis. We plot gain versus M, the number of models, in the quadratic minimization setting for n equal to 24 clients and up to m equal to 12 for different values of E. We get that gain increases with M almost linearly and even for the case of E equal to 1. Now I'll present the results of experiments we did on federated datasets. We worked on two kinds of problems, first being logistic regression and the second being binary image classification. Logistic regression is an example of convex optimization, while the binary image classification is an example of non-convex optimization as it uses CNNs. Further, we run experiments for both full device participation and partial device participation. Here are the results for full device participation. We plot for both training data and test data and see that gain increases with M for both logistic regression and binary image classification. For full details of the experiments, you can refer to our paper. In the case of partial device participation, we don't observe an always increasing gain with respect to M, but we nevertheless see that gain is always significantly greater than 1, which is still a good enough practical result. The key takeaways from these experiments is that even for the non-convex setting, we get an increasing gain for the full device participation. And even for the partial device participation case, we have gain significantly greater than 1. Finally, we simulate a realistic scenario where each model is actually a different task. Here, there are two kinds of examples. First, where the models are somewhat similar to each other, which is the case we did for binary image classification. Second, we did an experiment where one model is logistic regression while the other model is a convolutional neural network. First, we see the first we see the results for the case of similar models, and we see that for 9 different CNN models, we get a gain of 3.8 in training data and 3.57 for testing data. And for the case of completely different models, we get a gain of 2 in case of training data and 1.41 in case of testing data. For your time, I'm happy to take questions now.